Imagine a world where every extra layer of intelligence you add to a machine doesn't make it smarter, but actually makes it worse. Imagine pouring hours, days, even weeks of training into a deep neural network, only to watch it perform worse than a simpler one. It sounds impossible, right? Like adding more gears to a machine that should run smoother, only for it to break down faster. But that was the strange reality haunting computer vision back in the mid-2010s. Researchers were pushing deeper and deeper architectures, chasing better accuracy and richer representations, and suddenly, nothing worked. The deeper networks weren't learning more, they were failing harder. Accuracy tanked. Training error went up, not down. Models degraded simply because they had more layers, and nobody knew why. This is the moment our story begins. A moment when the entire deep learning community was staring at a wall no one knew how to climb. And then, a group of researchers at Microsoft Research asked a question so simple, so elegant, so shockingly effective that it permanently changed the direction of AI. They asked, what if the network doesn't need to learn everything? What if it only needs to learn the difference? And that idea gave birth to one of the most influential architectures in the history of machine learning, the residual network, or ResNet. Today, we're diving into the groundbreaking paper, Deep Residual Learning for Image Recognition, the research that solved the degradation problem, won the ImageNet competition, and paved the way for the explosive growth of deep learning models that power everything from self-driving cars to facial recognition to your phone's camera. And before we jump into this wild story, make sure to like this video, subscribe to the channel, and hit the notification bell so you never miss another deep dive into the papers that shaped AI. Alright, let's get into the idea that changed everything. To understand why this paper was revolutionary, you need to picture the mindset of deep learning researchers in 2014 and 2015. Depth was king. AlexNet blew up the field with 8 layers. VGG pushed to 16 and 19 layers, and deeper models consistently outperformed shallower ones. So naturally, everyone asked, what happens if we go even deeper? 30 layers? 50? 100? Intuition said deeper networks should be better. They have more parameters, more representational power, more room to extract subtle features. But reality had other plans. As researchers stacked more layers, they noticed something bizarre. Accuracy stopped improving and then started getting worse. And not just worse on the validation set, worse on training data too. That was the alarming part. It wasn't overfitting. It was as if the deeper network simply could not learn a good solution at all. In one example from the paper, a 56-layer plain convolutional network performed worse than a 20-layer version. Imagine tuning all these layers, only for your model to throw up its hands and say, I don't know what to do with this. This wasn't a vanishing gradient problem. Batch normalization had already solved most of that. The gradients were fine. The activations were fine. Optimization was still failing. This was the degradation problem. Deeper networks just refused to optimize properly. And that posed a fundamental question. If a deeper model literally contains a shallower one inside it, why can't it just learn to do at least as well? Why is depth suddenly the enemy? Enter the idea of residual learning. The authors of this paper realized something profound. Maybe layers shouldn't be forced to learn a full complex mapping from scratch. Maybe each set of layers should only learn the difference between the input and the desired output. Instead of trying to learn h of x, let the network learn f of x equals h of x minus x, the residual. Then the output becomes f of x plus x. In other words, the network gets to say, start with the input. Now here's how I want to adjust it. These adjustments, small nudges, are much easier for optimization to handle. And if a block doesn't need to do anything, the residual becomes 0, and the block simply acts as identity. This is why the skip connection, the identity shortcut that bypasses the convolutional layers, is so powerful. It ensures that information can flow freely through the network without getting distorted or crushed by unnecessary transformations. Suddenly, adding more layers didn't hurt performance. It improved it. The deeper you went, the better the model performed.
This was the breakthrough the field desperately needed. Now picture the architecture. Instead of a stack of convolutions, activation, and hoping everything works, each block looks like this. Take the input x, pass it through a couple of convolutional layers to compute f of x, then add the original x back in. The sum goes through a ReLU, and on you go to the next block. That simple addition, just a plus sign, created a direct path for information and gradients to travel through the network. It's like giving the model a safety net. No matter what happens inside the block, the identity path preserves a clean signal. And because the residual often ends up being small, something the authors proved experimentally, the model doesn't need to twist itself into a pretzel to find useful transformations. Instead, each block gently refines the representation, layer by layer, like a sculptor polishing the same statue over and over, rather than building a new one from scratch each time. But here's where things get truly exciting. Once you add skip connections, you can scale depth dramatically. The paper presents not just 18-layer and 34-layer networks, but 50-layer, 101-layer, and even 152-layer ResNets. And unbelievably, these extremely deep networks are actually easier to train than shallower plane networks.
The 152-layer ResNet became famous as the model that dominated the ImageNet 2015 competition, achieving 3.57% top 5 error, superhuman performance. And here's the twist. Despite being 8 times deeper than VGG19, it uses fewer floating point operations. Deeper, more accurate, and more efficient. That is the power of the bottleneck design introduced in this paper. Instead of using 2 3x3 convolutions per block, the deeper ResNets use a bottleneck structure, 1x1 convolution to reduce dimensionality, 3x3 to process it, and another 1x1 to restore it. This trick reduces computation while still allowing the network to learn rich transformations. And it doesn't stop with ImageNet. When the researchers applied ResNets to CFAR-10, they built networks with 20, 32, 44, 56, and even 110 layers. The deeper the network, the better the test accuracy, until they pushed it beyond 1,000 layers. Yes, they trained a 1,202-layer ResNet. And here's the wild part. It didn't fall apart. It actually reached near-zero training error. The only reason it didn't achieve the best test accuracy was simple overfitting on a small dataset. Optimization, however? No problem. This result shattered the old belief that extremely deep networks were inherently too difficult to optimize. Residual connections proved that depth wasn't the enemy, the architecture was. Beyond classification, the authors also tested their ResNet features in object detection tasks like faster RCNN using Pascal VOC and MS COCO. The results were staggering. Simply swapping out VGG16 for ResNet 101 increased COCO's MAPAT by 28%. No fancy tricks, no extra modules, just a better backbone. The model became state-of-the-art across ImageNet detection, localization, COCO detection, and COCO segmentation. This wasn't just a small improvement, it was a total reshaping of what was considered possible. But perhaps the most beautiful evidence supporting the residual idea comes from analyzing the activations inside the network. When the authors examined the magnitude of residual outputs across layers, they discovered that deeper networks produced smaller residuals per block. In other words, as the network grows deeper, each layer doesn't perform a massive transformation. Instead, it makes a tiny correction, a slight adjustment, exactly what the theory predicted. Depth becomes less about stacking big transformations and more about accumulating thousands of subtle, intelligent refinements. That's what makes residual learning not just effective, but elegant. Think about the philosophical shift this introduced. Before ResNets, training deeper models felt like trying to force every layer to reinvent the wheel. After ResNets, depth became a matter of refinement. Instead of rebuilding the world from scratch, each layer now collaborates with its previous ones, offering small suggestions, improving the representation step by step. The skip connection is more than a technical trick. It's a communication channel that keeps the network grounded. And because gradients can flow easily through skip connections, training no longer collapses as networks grow deeper. Today, the influence of this paper is everywhere. Modern architectures like DenseNet, ResNets, CNet, EfficientNet, and even many transformers draw inspiration from the idea of shortcut connections and residual pathways. The concept is fundamental, almost obvious in hindsight, yet profoundly transformative. It's one of those rare breakthroughs that feels like it should have always been there, something that changes your understanding of neural networks the moment you see it. So if you've ever wondered how we went from shallow CNNs to the gigantic architectures powering modern AI, this is the paper that made that leap possible. Residual learning didn't just solve a technical problem, it opened a new frontier. And the best part? The core idea is so simple you can write it in one line. Output equals f of x plus x. That tiny equation changed the world. If you enjoyed this deep dive into one of the most important papers in AI history, go ahead and smash that like button, subscribe to the channel, and leave a comment telling me which paper you want to explore next. Your engagement helps this channel grow and reach more people who love understanding the breakthroughs shaping our future. Thanks for watching, and I'll see you in the next video.